It's Jono from Seneca. This is the second time I am trying to record this revision episode. Tried the first time, had a breakdown, now we're here. Good luck for your exams. I'm covering everything you need to know for chemical analysis for GCSE chemistry. And breathe. It's going to be great. It's going to be fine. It's going to be fine. I'm excited. Where are we starting? We are starting with purity and formulations. How pure, how chaste, how delightful. What's a pure substance? Well, a chemically pure substance is a single element or compound, just one. It contains only one substance. Purity is worked out by looking at the melting and boiling points of samples. Here are some examples of pure substances. So some examples of pure substances are water, copper sulfate, glucose, oxygen gas, sodium chloride. Those are all pure. And to work out purity, we look at the melting and boiling points of substances. Pure substances have specific melting and boiling points. The closer the values of your experiment are to those in the data book, the purer the sample is. Melting points. Impurities lower the melting point and increase the range of temperatures at which the sample will melt. And impurities increase the boiling point and increase the range of temperatures at which the sample will boil. Bam! So remember, that's a pure substance is defined as in chemistry as a single element or compound, and they have exact and specific melting and boiling points. So let's go over some formulations now. They are a mixture of chemicals that are designed to create useful products. In a formulation, each component helps to decide what the mixture's overall properties are. Synergy, work together, we love it. Quantity of each component. To ensure that a formulation does what it is supposed to, each chemical component must be present in a precisely measured quantity. Examples. Formulations are everywhere. Left, right, up. There's maybe one behind me. I don't know. Examples include agents, fuels, metal alloys, fertilizers, and medicines. So remember, to summarize, formulations are mixtures of chemicals that are designed to create useful products. So some facts about formulations. Every component affects the overall properties, and the quantity of components is precisely measured. That is precise. So precise, specific, amazing. So what do we call mixtures of chemical components that are designed to create useful products? That is a formulation. Remember that key definition. Now, do remember impurities? Impurities increase a sample's boiling point and increase the range of temperature at which a sample will boil. Okay, next we're going to talk about some cute chromatography. It's a process that separates mixtures into different components. There are two phases, honey. First of all, we come up with the substances that are picked up and they're carried by a mobile phase. That mobile phase is going to be a liquid or gas. Think about it. Solids can't move. So the mobile phase has got to be a liquid or gas. The mobile phase then moves through a stationary phase, which is a solid or a viscous liquid. Viscous means thick. That word also comes up in our organic chemistry, everything you need to know episode. So make sure you check that out. Who doesn't love a cute little plug? Separation of substances. Let's go. This depends on the distribution of a substance across the two phases. A substance moves far if it's attracted to the mobile phase. A substance doesn't move far if it's more attracted to the stationary phase. The laws of attraction. Strength of attraction. Different components can sometimes be equally attracted to a solvent. Therefore, the number of spots a mixture produces can vary depending on the solvent used. I love it. So, quick question. In chromatography, will a substance move further if it is more attracted to the mobile phase or the stationary phase? It's if it's more attracted to the mobile phase, okay? How many chromatography spots are produced by pure samples? This is a nice little exam question. Get you in the zone. Get ready for that exam, okay? So it will be just a single spot. And this is because the definition of a chemically pure substance is that it consists of only a single element or compound. This means that pure samples will only ever produce one chromatography spot, regardless of solvent identity. Can you believe it? Look at us bringing together everything that we've covered so far in one nice little exam question. Okay, let's review. How do impurities affect the melting point of a sample? Well, I'm glad you asked. It reduces that sharpness of the melting point, okay? So that is what impurities do. And do remember what formulations are. They are mixtures of chemical components that are designed to create useful products. Fantastic. Okay, and there's two phases of chromatography. We've got the stationary phase, which can be a solid or a viscous liquid, and we have the mobile phase, which is a gas or a liquid. Okay, so we've talked a little bit about chromatography, but we're going to go even into more detail. Can you believe it? I'm excited. Are you excited? I'm so excited. Why am I excited? Because we're talking about paper chromatography. I love paper. I love chromatography. So this is going to be a riot. In paper chromatography, mixtures of soluble substances are separated. A solvent, mobile phase, is run through the mixture on paper containing the stationary phase. The substances will then move up the paper at different rates. The most soluble substances will move the furthest up the paper. So honey, what are our steps? 1, we dip that chromatography paper. We dip the bottom of the chromatography paper into the solvent. What next? Solvent movement. The solvent travels up the chromatography paper. It's moving on up. As the solvent moves, it picks up the substance being tested and carries the substances up the chromatography paper. Distance travel. The components that travel furthest are highly soluble, dissolve easily in the solvent. They are also minimally attracted to the chromatography paper. Okay, so in paper chromatography, the components that travel furthest are minimally attracted to the chromatography paper and are highly soluble in the solvent. Fantastic. Now, what is a chromatogram? So many new words, so many keywords. It's a lot to deal with. Chromatography produces chromatograms. So that's what we produce in chromatography. We use these to identify compounds and mixtures by calculating RF values. RF is the distance traveled by a substance divided by the distance traveled by the solvent. Remember that key equation. Distance traveled by the substance divided by distance traveled by the solvent. And we can work this out for both reference substances and tested substances. So let's talk about solvents to begin with. RF values depend on the solvent. We can learn more about the identity of the components by testing any references and the unknown mixture in a range of solvents. So what are these reference substances I keep on barking on about? Well, a reference substance is a pure sample that's run alongside the unknown mixture to see if it's a component in the mixture. These substances provide valuable evidence, but not proof, okay? That was such an important point, I even thwart my fam. Remember, reference substances provide evidence, but not proof, okay? So RF, let's reiterate, it's the distance traveled by the substance divided by the distance traveled by the solvent. Remember, it's the distance traveled, and make sure they're in the same units. So let's go over the steps of the paper chromatography practical. I bet you can't wait to do this. It's such a fun practical. The practical investigates the use of paper chromatography in separating mixtures. The process is as follows. 1, use a pencil to draw a horizontal line near the bottom of the chromatography paper. 2, on the start line, put samples of known food colorings A, B, C, and D alongside an unknown substance. We're going to call that substance X. Place the paper in a beaker containing a small volume of solvent. Wait for the solvent to travel up near the top of the paper. By comparing spots produced by X with these produced by A to D, it should be possible to identify the unknown substance. So great, so fun, so amazing. It's just who doesn't love a step? So what can we say if the RF values of a reference substance and a spot match in all solvents? Okay, we can say that it's very likely the mixture contains the reference compound. We can't be certain. We can't use the word prove, okay? So if the RF values of a reference and a spot match, so the RF values of one of our reference substances and the RF value of our unknown solvent are the same, we can say it's very likely that the mixture contains the reference compound, but we can't say it for certain, okay? What is the mobile phase in paper chromatography? It is a solvent, remember? So a solvent is just something that dissolves something else. Okay, right. So that was a nice quick run through paper chromatography. So I think we're gonna do something fun now, okay? Are you ready? Are you ready? I hope you're ready, because I'm ready. We're gonna go over the identification of common gases, but we're gonna do it in a hyper learning format. It's gonna be crazy, it's gonna be fast, it's gonna be everything you need to know, efficient revision. You're gonna boss it. You're gonna absolutely kill that exam. Let's go. Testing for hydrogen. Oh, that was my chair making that noise, but it was a kind of a squeaky pop. That's maybe a little bit of cross-cutting to let you know what's coming. Ooh, so exciting. Testing for hydrogen. The presence of hydrogen gas can be tested by holding a lit splint at the open end of a test tube containing a gas. So lit. If the gas is hydrogen, a squeaky pop sound will be produced like a... It doesn't sound like that, but you get what I mean. Next, testing for oxygen. The presence of oxygen gas can be tested by inserting a glowing for the gods splint into a test tube containing a gas. And what happens if we do that? Well, if the gas is oxygen, the splint will relight. Like that said, relight my fire. Boom, featuring Lulu. It's a classic song. If you don't know it, look it up. So, how do we test for the presence of oxygen gas? We insert a glowing splint into a test tube containing a gas. You have to use the word glowing. It's not unlit, it's not lit, it's a glowing splint, okay? Next, we're going to talk about carbon dioxide. The presence of carbon dioxide gas can be tested by bubbling a gas through or shaking carbon dioxide with an aqueous solution of calcium hydroxide. Now, calcium hydroxide is also called lime water, okay? Let's consolidate some of the stuff we've covered. The presence of oxygen can be tested by inserting a glowing splint into a test tube containing a gas. If the gas is oxygen, the splint will relight. Love that, okay? And let's finish off talking about carbon dioxide. So we bubble a gas or we shake a gas with lime water, and if carbon dioxide is present, the solution will turn cloudy. It will go from clear to cloudy. Okay, how do we test for chlorine? Well, the presence of chlorine gas can be tested by inserting a damp litmus paper into a test tube containing a gas. Damp litmus paper sounds disgusting. So, to test for chlorine, what do we do to test for chlorine? Well, I am glad you asked. So we take our damp litmus paper, and if the gas is chlorine, it will bleach and change color from red to white. So the damp litmus paper will go from red to white if the gas is chlorine. So that is how we test for chlorine. So fun. So we've gone over some really important gas tests, but let's do some questions to consolidate what we've covered. Are you excited? I'm so excited. Which of these gases is tested for by placing a glowing splint inside a test tube? Oxygen, hydrogen, carbon dioxide, or chlorine? You know this. I know you know it. It is oxygen. It is oxygen. And it's going to be hydrogen because the question said a glowing or lit splint. So that glowing splint tests for oxygen and it will relight. And that lit splint will test for hydrogen and we'll get a squeaky pop, squeaky pop. So that was some identification of common gases. Now, that was quick fire. That was fun. I'm still a little bit shaky from it because that's how much fun it was. But I want to keep going. I'm going to keep going. We're going to do some flame test hyperlearning now. It's going to be wild. What a flame test, I hear you ask? Well, let me tell you. Let me break it down to you step by step. So flame tests are used to identify metal ions. Metal ions can be identified as they will burn with a characteristic color. All the colors of the rainbow, honey. Let's go. So lithium will burn with a crimson flame. Crimson, it's like a deep, beautiful pink. It's stunning. Potassium K+ burns with a lilac flame. It's my mom's favorite color. We love a bit of lilac. So what color was lithium again? Do you remember? It is crimson. Make sure you use the word crimson. Even if you don't know what crimson looks like, just make sure you write crimson. Don't write deep red. Don't write pink. It's crimson. Calcium Ca2+ that burns with an orange-red flame. Orange-red. Do you remember what color potassium burns with? Shout it out to me. It's lilac. You know it's lilac. Copper burns with a green flame and sodium burns with a yellow flame. So which metal ion burnt with an orange-red flame? Can you remember? It is calcium, Ca2+. Burn, baby, burn. So which ions burn with a crimson flame? Honey, that is lithium. Potassium burns with a lilac flame. And with a green flame, that is copper. So copper ions burn with a green flame. Sodium ions burn with a yellow flame. And orange-red flame is calcium. Okay? So let's go over the flame test practical now, because we all know we love practical chemistry. We can use flame tests to identify metal ions in a single ionic compound. What are our steps? Step 1. Start the experiment by cleaning a nichrome wire loop by submerging it in dilute hydrochloric acid. Oh, it's so dramatic. I love it. Step 2, the wire loop is then dipped into the sample to be tested. Dip. Then step 3, the wire loop is held in a blue flame. It's a blue flame, not a yellow flame. We want complete combustion up in here. We held that wire loop in the blue flame and the color is recorded. Let's go over those 3 steps again. Step 1, we get a nichrome wire loop and we clean it by submerging it in dilute hydrochloric acid. The wire loop is then dipped into the sample to be tested. The wire loop is then held in the blue flame of a Bunsen burner and the color is recorded. So why do we submerge that loop in hydrochloric acid? it removes impurities that could affect the flame color. Let's go over those colors again. They're so important. Guaranteed marks. Let's do it. Sodium ions, what color do they go with? They go with a yellow flame. Copper ions go with a green flame. Lithium, crimson. Calcium, orange, red. Okay, sentence completion. Are you ready? So, the acid we use to clean the loop is hydrochloric acid. We then dip the wire loop in the sample to be tested. We hold it in a blue Bunsen burner flame and we record the color of the Bunsen burner flame. Bam! Oh gosh, my fan is broken. It's okay though. The other side works. What? Boom, we just absolutely annihilated that flame test hyperlearning. Like, so good, so excited. But we've got some more to do. We've got some more to do, honey. Let's go. We're talking about metal hydroxides next. I love metal hydroxides and forming precipitates. It's so much fun. Even the word precipitate, I'm like, yeah, precipitate, procrastinate, elevate, let's do it. Metal hydroxide. Aqueous solutions of metal compounds contain metal ions. These ions can come out of solution when they react with a sodium hydroxide solution. That's sodium hydroxide, NaOH. This produces insoluble salts. They don't dissolve in water, and we call those precipitates. Aluminium ions, A3+, they form a white precipitate, aluminum hydroxide. Al3 plus 3OH minus goes to Al brackets OH close brackets 3. Unlike the other two white precipitates, which we're going to be covering a little bit later, aluminium hydroxide dissolves in excess NaOH to give a colorless solution. So basically, if we chuck loads of sodium hydroxide into the solution, that white precipitate will dissolve. Calcium hydroxide, also a white precipitate, Ca2 plus 2OH minus goes to Ca open brackets OH close brackets small little 2. If we're doing state symbols, remember those ions, the Ca2 plus and OH minus, are going to be aqueous, but that precipitate is going to be solid. You need to include that S. Next, we're doing magnesium hydroxide, the third and final white precipitate. Magnesium Mg2 plus 2OH minus goes to Mg open brackets OH close brackets 2. Fantastic. So, next, let's fill in some gaps to consolidate our learning. Aqueous solutions of metal compounds contain metal ions. These ions can come out of solution when reacted with sodium hydroxide solution, and this produces insoluble solids called precipitates, okay? Love that. Okay, we've got some more to do. We've got some more colors coming. Honey, it's going to be a ride. I'm excited. Are you excited? Let's go. We're going to start with copper 2 hydroxide. The 2 tells us the oxidation state of the copper. So that means the copper has a 2 oxidation state. Copper ions Cu2 plus form the blue precipitate copper brackets 2 hydroxide. Cu2 plus 2H minus goes to CuOH2, and that OH is in brackets. Iron 3 hydroxide forms a brown precipitate, and iron 2 hydroxide forms a green precipitate. Remember those colors, okay? That is what we need. So what were those colors again? Let's go through them so they stick. Copper 2 hydroxide is blue, iron 2 hydroxide is green, and iron 3 hydroxide is brown, okay? So those are the hydroxides you need to remember. We've gone over some beautiful, cute little precipitates, and I love it. It's great. But do you think we're done? Oh no, we got some more to do. We need to know carbonates, halides, and sulfates. Oh my God, the exam board is not being kind to you. So much slang, but we're going to make this fun. We're going to go through it. You're going to feel great about it. You're going to listen to it before your exam, maybe on the bus, and you're going to go in and boss it. So let's go. How do we test for carbonates? Carbonates are compounds that contain CO3 2 minus ions. Carbonates react with dilute acids to form a salt, carbon dioxide, and water. So it's going to effervesce. It's going to bubble and give gas. Let's go through an example. Calcium carbonate plus hydrochloric acid goes to calcium chloride plus carbon dioxide plus water. As carbon dioxide is produced, we can use the standard carbon dioxide test to work out if an unknown substance is a carbonate. Do we remember that test? It is the lime water test. Bubble that gas through lime water and it's going to go from clear to cloudy. So great. So when we react a carbonate with a dilute acid, we produce 3 products. That's 1, 2, 3 products. And what are they? Water, a salt, and carbon dioxide, CO2. So how can we confirm that carbonates produce carbon dioxide? We can use the lime water test. We bubble the gas through lime water, and if it goes cloudy, we have produced CO2. Amazing, fantastic, stunning, groundbreaking, revolutionary. What about halides? Well, halide ions are negatively charged, so they are anions. A negatively charged ion is an anion. And there are 2 steps to halide testing. 1, don't pick up the phone, just kidding. 1, add dilute nitric acid to an unknown solution. This gets rid of those carbonate ions. because carbonate ions could disrupt the test by forming a precipitate with the silver ions added in step 2. So what do we do in step 2? Well, unsurprisingly, we add silver nitrate. So silver nitrate can help us detect the halide ions because if they're present, they will form a precipitate with the silver ions. And there's 3 we need to go over. First one is silver. If there is, of course there's silver ions. Haha. The first one is chloride. If there are chloride ions present, we form silver chloride, which is AgCl and it's white. If bromine ions are present, bromide ions are present, we form silver bromide, which is AgBr. If iodide ions are present, we form silver iodide, AgI, which is pale yellow. I'm going to go through those again very quickly. So AgCl is with chloride ions and is white. AgBr is with bromide ions and is a cream color. AgI is a yellow color. So that's silver iodide is yellow. I always think of it, if we start with chlorine, we're then going down the halogens and the color's getting like kind of darker and darker. It starts at white, it goes cream, and then it goes yellow. And that's going down the periodic table, down group 7. That's how I remember it. Maybe it's helpful, maybe it's not. If it's not helpful, make a cute little flashcard and just remember that AgCl, white, AgBr, cream, AgI, pale yellow, okay? And what are the 2 steps? Firstly, we add dilute nitric acid to get rid of carbonate ions, and then we add silver nitrate. So we're going to test for sulfates next. And this is our final thing to go over. Are you excited? I'm so excited. I'm so ready. I'm pumped. To test for a sulfate is SO4 2- ions. We add dilute hydrochloric acid. Why do we do this? It removes carbonate ions. Goodbye, carbonate ions, because these could disrupt the test results by forming a precipitate with the barium ions added in step 2. Again, I've already alluded to what we're going to be doing next. We're going to be adding barium chloride. So we add barium chloride to the solution, and if sulfates are present, the white precipitate barium sulfate will form. So Ba2 plus SO4 2- goes to BaSO4. Amazing. Okay, so that was a lot of information, a lot to take in. I hope it was useful. Let's just have a few questions to finish. So what ions do carbonate contain? It's CO3 2-, one of those key ions you need to know. How many steps are there in halide testing? It is 2 steps in halide testing. First, we add dilute nitric acid to get rid of carbonate ions, and then we add silver nitrate. Do you remember why we need to get rid of those carbonate ions? It's because they could react with the silver that is added in step 2. So we've got to get rid of them, okay? So those are the steps involved in testing for a halide. It's quite similar for a sulfate, but with a sulfate, we add dilute hydrochloric acid, and then we add barium chloride. Stunning, absolutely stunning. So great. So that brings us to the end of this episode. I hope it was useful. We've run through a lot. Hope it was I hope it was enough detail, and I hope it was still engaging enough. Best of luck with all of your studies. If you have exams coming up, best of luck, and even more like reason to be done. Summer is just around the corner, so close. Best of luck. Thank you so much for joining, and I will catch you on the next episode. I've been Jono from Seneca. Thank you. Bye.